So, let us continue the discussion on the equivariant estimators and maximal invariants. I had considered one example of the finding out maximal invariant. Let me take one or two more examples also. So, let us consider say again X as n dimensional Euclidean space and G is the group of scale transformations. So, I am considering for n points, then G C of x is equal to C x 1, C x 2, C x n, where C is any positive real number. In this case, T x is equal to x 2 by x 1 and so on, x n by x 1. This is a maximal invariant. Once again, you can see that as x 2 goes to C x 2, x 1 goes to C x 1. So, this ratio becomes same as x 2 by x 1, x n goes to C x n, x 1 goes to C x n. So, the ratio goes to x n by x 1 etcetera. So, these are all, this is an invariant function. So, clearly T x is invariant, and also if I take 2 points T x is equal to T y, then what I get x 2 by x 1 is equal to y 2 by y 1, x 3 by x 1 is equal to say y 3 by y 1 and so on, x n by x 1 is equal to say y n by y n. Then this implies x 2 is equal to y 2 x 1 by y 1, x 3 by x 3 is equal to say y 3 into x 1 by y 1 and so on, x n is equal to y n into x 1 by y 1. So, this is C. So, this implies that x is equal to G C of y, where we have chosen C to be x 1 by y 1. So, T is maximal invariant. Let us take another example, say x is equal to say R n and G is the group of all n factorial permutations of coordinates of x. Then T x is equal to order statistics x 1, x 2, x n. This is maximal invariant. Now, let us look at the importance of invariance in determining the best. As I mentioned earlier, that we want to use this concept to reduce the class of available estimators, and in that reduced class, if it is possible to find the best one, then we are having some sort of optimal estimator in that class. Now, when we start the reduction, then we have to find out the equivariant estimator. We have seen one example here in the binomial case. The condition that we are getting here is that we should have T of n minus x is equal to 1 minus T of x. In the case of uniform distribution, we got the form of the equivariant estimator as a multiple of x. Now, if you take multiple of x, then you realize here, for example, 2 x is unbiased. It is also the method of moments estimators for this problem. But suppose I have n observations x 1, x 2, x n. In that case, if I straightforwardly apply the concept of invariance, then the estimator will turn out to be a function of, it will turn out to be x 1 into a function of x 2 by x 1, x 3 by x 1 and so on. On the other hand, we had seen that the maximum likelihood estimator is x n, the complete sufficient statistics is x n. Now, in that case, why not we restrict attention firstly to the sufficient statistics and then we apply the concept of invariance. So, let me justify this thing, sufficiency and invariance. So, there is a natural question that when the two criteria of sufficiency and invariance are there, then which one should be applied first? Can the applications of these in any order give the same answer, or that will lead to the same solution, etc. The general answer to these questions have been attempted by many researchers, and under certain conditions certain results have been obtained. But we will follow a practical approach here. In most of the estimation problems, we usually deal with convex loss functions. If the loss function is convex, the class of estimators which is based on the sufficient statistics supersedes, or you can say, given any estimator which is not based on the sufficient statistics, we can find an estimator which is better than that using the Rao-Blackwell theorem. Therefore, we can restrict attention to the class of estimators which are based on sufficient statistics. Now, if we apply the invariance on this class of estimators, then we are considering much smaller class. So, we will follow this approach here. So, we usually apply the principle of sufficiency first and then apply the principle of So, let us see in certain problems when the group of transformations is transitive, we may actually end up with getting the best equivariant estimator. So, let us start with the uniform distribution problem. Suppose we have let me firstly consider this x following uniform 0 theta problem which I introduced earlier. We got the form of the group was a scale group, that is GCX is equal to Cx, where C is positive, here theta is positive. The form of a scale equivariant estimator is given by, let me use the term d delta k, that is equal to k times x. We want to minimize the risk of delta k with respect to k. So, let us consider the risk of delta k, that is equal to expectation of k x minus theta square, sorry, k x by theta minus 1 square. Let us substitute, say, t is equal to x by theta. Then what is the distribution of t? That is uniform 0 1. So, we can write it as expectation of k t minus 1 square. That means, the risk function of the best equivalent of the equivalent estimator is independent of the parameter. Now, this is True, because this scale group of transformations is a transitive group, because if I consider any 2 points theta 1 and theta 2 on the positive real line, then they can be reached from the other one. For example, I take theta is equal to 2 and theta 1 is equal to 2 and theta 2 is equal to 3. Then if I choose c is equal to 3 by 2, then 3 by 2 times 2 is equal to 3. That means, there exists a transformation, so that I can reach theta 2 from theta 1. Therefore, the risk function will be constant, and therefore, we can find out the best choice here. So, this is now naturally a convex function of k, and so the minimum occurs when del r by del k is equal to 0. Now, this del r by del k is equal to 0, you can calculate del r by del k, that will give us twice expectation k t minus 1 into t is equal to 0. This means, k is equal to expectation of t by expectation of t square. Now, in the case of uniform distribution, the mean is half and expectation t square is 1 by 3, that is equal to 3 by 2. So, 3 by 2 x is the best scale equivariant estimator of theta. Now, let us just have a comparison between various estimators for this problem. See, let me give the notations here. Say d 1, that is 2 x, which is actually equal to delta 2 under this notation, because delta k is k x. So, this is method of moments estimator here. And d 1 sorry d 2, that is equal to x, that is equal to delta 1 is the maximum likelihood estimator of theta, and this is d 3, that is equal to 3 by 2 x, that is actually delta 3 by 2. This is the best scale equivariant estimator of theta. Naturally, d 3 is better than both d 1 and d 2, better than both d 1 and d 2. Also, let us compare d 1 and d 2. What is the risk of d 1? That is equal to expectation of 2. So, actually we have the general form here. We can calculate the risk function of delta k, that is expectation of k t minus 1 square, that is equal to k square expectation of t square minus twice k expectation of t plus 1, that is equal to k square. Expectation of t square is 1 by 3 minus twice k, expectation of t is half plus 1, that is equal to k square by 3 minus k plus 1. So, from here the risk function of the method of moments estimator, that will be equal to 4 by 3 minus 2 plus 1, that is equal to 1 by 3. The risk function of d 2, that is the maximum likelihood estimator, that is the risk of delta 1, that is equal to 1 by 3 minus 1 plus 1, that is equal to 1 by 3, and the risk of d 3, that is the best scale equivalent estimator, that is obtained by putting k equal to 3 by 2, that is equal to 9 by 4 into 3 minus 3 by 2 plus 1. So, that is equal to 1 by 4, which is less than 1 by 3. So, in this particular case, the method of moments estimator and the maximum likelihood estimators, they have the same risk, and the best scale equivalent estimator is better than both of them. So, here you can see the concept of invariance helps us in reducing the mean squared error, because here the risk criteria is actually the mean squared criteria, mean squared error criteria. Now, I will generalize this problem. Here I have considered only one observation from the uniform distribution. Now, in place of one observation, suppose I have n observation. Let us consider generalization to n observations. If I have generalization to n observations, that is x 1, x 2, x n follows uniform 0 theta. The loss in estimating theta is once again the same I am considering to keep the problem invariant. The group of transformations is the scale group of transformations. Now, here x n is, let me call it say t, is complete and sufficient. Rather, okay, let me call it y, and we know the distribution of y. The distribution of y is n y to the power n minus 1 by theta to the power n. Then the distributions f y theta for theta greater than 0, they will remain invariant, because if I consider the distribution of, see, if I take g c of y, then that will be equal to c of y, because if each of the observations is shifted by c x, then x n, that is the maximum, will also be shifted by c. So, x n goes to c x n, and therefore, theta will go to c theta for this density also. Therefore, this density family of distributions is invariant under the scale group of transformations, and same thing will happen to the a also, that is g c tilde a, this will become equal to c a. Theta goes to c theta and a goes to c a. So, we can consider the form of scale equivariant estimator based on y, because this is the complete sufficient statistics. So, rather than starting from x 1, x 2, x n, we will initially itself restrict attention to x 1, that is the x n, that is the sufficient statistic. So, this is obtained by considering the condition, that is d of g c y equal to g c tilde of d y for all y and for all c. Now, this condition gives d of c y is equal to c of d y. So, you can choose c is equal to 1 by y. So, there is no invariant here, actually no maximal invariant here. You will get d of 1 is equal to 1 by y d of y. This implies d of y is of the form, this d 1 is a constant times y. So, we can write the form of a scale equivariant estimator is then, let us call it delta k of y is equal to k times of y. In fact, if I consider delta 1 that is equal to y, this is the maximum likelihood estimator, and if I take delta is equal to n plus 1 by n, that is n plus 1 by n y, this is the minimum variance unbiased estimator of theta. So, these two things are known to us. Now, let us try to see whether I get something else by considering the minimization of the risk function with respect to k. So, let us consider the risk function of delta k, that is equal to expectation of k y by theta minus 1 square. See, once again we can look at this density. If I define say t is equal to y by theta, then the density of t is nothing but n t to the power n minus 1, 0 less than t less than 1, 0 otherwise, because this is the density of y. So, if I consider the density of y by theta, then 1 by theta dy will be equal to dt. So, this density reduces to n t to the power n minus 1. So, if I look at expectation of t, that is equal to integral n t to the power n dt 0 to 1, that is equal to n by n plus 1, and expectation of t square turns out to be 0 to 1 n t to the power n plus 1 dt, that is equal to n by n plus 2. So, this is equal to expectation of k t minus 1 square. If we consider the minimization with respect to k, r is minimized with respect to k if del r by del k equal to 0. Why? Because this is nothing but a convex function of k. This is convex function of k. So, this del r by del k, this gives twice expectation k t minus 1 into t equal to 0. That means, k is equal to expectation of t by expectation of t square, and that is equal to n by n plus 1 divided by n by n plus 2, that is equal to n plus 2 by n plus 1. So, delta of n plus 2 by n plus 1, that is n plus 2 by n plus 1 y, is the best scale equivariant estimator of theta. Once again we can look at the relative risk comparison or risk improvement here. Naturally, here you have the coefficient 1, here you have coefficient n plus 1 by n, and here you have n plus 2 by n plus 1. So, this is the best, that is the risk of this will be the smaller than both of this. Now, let us look at the overall comparison of the risk values here. So, what is the value of r theta delta k, that is k square expectation of t square minus twice k expectation of t plus 1, that is equal to n by n plus 2 k square minus twice n by n plus 1 k plus 1. So, if I look at the risk of say the maximum likelihood estimator, here k equal to 1. So, I get n by n plus 2 minus twice n by n plus 1 plus 1. So, you can simplify this, that is equal to n square plus n minus twice n square minus 4 n plus n square plus 3 n plus 2 divided by n plus 1 into n plus 2. So, this gets simplified, that is equal to 2 divided by n plus 1 by n plus 2. If we look at the risk of the unbiased estimator, minimum variance unbiased estimator, then that is equal to, it is obtained by the value k equal to n plus 1 by n here. So, here if we substitute that, we get n by n plus 2, n plus 1 square by n square minus twice n by n plus 1 into n plus 1 by n plus 1. So, here these terms get cancelled out and we get here n square plus 2 n plus 1 divided by n into n plus 2, this is minus 1, because this is minus 2 plus 1, that is equal to once again 1 by n into n plus 2. So, naturally you can see that this is greater than. Okay, let us also look at the risk of the best scale equivalent estimator, that is equal to n by n plus 2 into n plus 2 square by n plus 1 square minus twice n by n plus 1 into n plus 2 by n plus 1 plus 1. So, this can be simplified, that is equal to n square plus 2 n minus twice n square minus 4 n plus n square plus 2 n plus 1 divided by n plus 1 square (1 by n plus 1 square). So, if we compare now this 1 by n plus 1 square less than 1 by n into n plus 2, okay, because this is n square plus 2 n and this is n square plus 2 n plus 1. So, dBs is better than dum. Similarly, if I compare the MLE and the UMVE, then 2 by n plus 1 into n plus 2 and 1 by n into n plus 2. Let us look at the comparison here. So, this term if I multiply, I get twice n square plus 4 n, and here I get n square plus 3 n plus 2. So, if I put greater than, this is reducing to n square plus n greater than 2. So, this condition is true, that means DUM is better than DML. So, in this particular case, the best scale equivalent estimator turns out to be the best among the 3 given estimators. Let us take the normal distribution case. X 1, x 2, x n follows normal mu 1, where mu is a real number. We consider the group of translations or the location transformations G C of x is equal to x plus c, where c is any real number. Now, you observe here that x I plus c, that will follow normal mu plus c 1. So, if mu is a real number, mu plus c is also a real number. So, the family is invariant. This family is invariant under the location group. Let us take the loss function here as mu minus a square. Now, if mu goes to mu plus c, a should go to a plus c. So, if I take a going to a plus c, then the loss function remains invariant, and therefore, the estimation problem is invariant. So, now let us find out the form of a location equivariant estimator this must satisfy. Now, in this problem x bar is sufficient. So, we will restrict attention to the distribution of x bar based on x bar. So, we will have T of x bar plus c is equal to T of x bar plus c for all c and for all x bar. So, you choose c is equal to minus x bar. So, you will get T x bar is equal to x bar plus a constant. So, we call it say d k, where k is any real number. So, this is the form of a location equivariant estimator, that it is x bar plus a constant. So, if I consider the risk function of this, that is equal to expectation of x bar plus k minus mu whole square, that is equal to expectation of x bar minus mu square plus k square plus twice k expectation of x bar minus mu. This is 0. So, you are left with 1 by n plus k square. This is minimized at k equal to 0. So, x bar is the best location equivariant estimator. Of mu. Let us generalize this problem. I consider here the variance also to be unknown, x 1, x 2, x n following say normal mu sigma square. Now, we maintain the same loss function. No, sorry, we change the loss function as mu minus a by sigma whole square. Let us consider the group of transformations which are linear or affine. A x plus b, where a is a positive number and b is any real number. This is called group of linear transformations or affine transformations. So, we use the notation G A. Now, under this the distribution of A x I plus b is normal A mu plus b a square sigma square. So, a mu plus b is another real number, a square sigma square is positive. Therefore, the family is invariant. The family of normal mu sigma square distributions, this is invariant under the group G A. Naturally, you are seeing that a mu goes to a mu plus b, a square sigma square goes to a sigma square goes to a square sigma square. Therefore, if I want to consider the, let me put here d, then d should go to a mu plus d. Then the estimation problem is invariant. Then the estimation problem is invariant under the group G. Now, to derive the form of a affine equivalent estimator, let us consider the form of an affine equivalent estimator. Then you will get d of x bar s square. So, here in this problem x bar and s square is complete and sufficient. So, a d x bar s square plus b is equal to d of a x bar plus b a square s square for all a and for all b and for all x bar and s square. So, you choose b is equal to minus a x bar and a is equal to 1 by s. Then this will give us d of x bar s square is equal to x bar plus some constant times s. So, this is the form of an affine equivalent estimator. Let us look at the risk function here. Let us consider the risk function of dk. That is equal to expectation of x bar plus k s minus mu by sigma whole square. That is equal to expectation of x bar minus mu by sigma whole square plus k square expectation of s square by sigma square plus twice k expectation of x bar minus mu s by sigma. Now, in the sampling from normal distribution, we know that x bar and s square, they are independently distributed. So, this term will become 0, because this will become expectation of x bar minus mu into expectation of s by sigma, and this is 0, as x bar and s square are independent in sampling from normal populations. So, this term simply becomes 1 by n plus k square, expectation of s square is sigma square. So, this is simply 1. Once again this is minimized when k equal to 0. So, x bar is the best affine equivariant estimator of mu. Suppose I take the loss function here, that means the problem is of estimating sigma square. If I consider this, then the estimation problem remains invariant. The estimation problem will be invariant under the affine group if d goes to a square d, because sigma square goes to a square sigma square. So, this will remain invariant if d goes to a square d. So, the form of an affine equivariant estimator for sigma square, this should satisfy delta of a x bar plus b a square s square is equal to a square delta of x bar s square. So, you choose b is equal to minus a x bar and A is equal to 1 by S. So, then this will imply that delta of x bar S square is nothing but a constant times S square, because this will become 0, this will become 1. So, where k is a positive real. Let us look at the minimization of the risk of delta k, that is equal to expectation of k S square minus sigma square by sigma square whole square. Let us use the notation W is equal to say S square by sigma square, that follows chi square n minus 1. Actually, it will depend upon what notation for S square I am using. If I am using S square is equal to sigma x I minus x bar whole square by n minus 1, then we should have n minus 1 S square by sigma square follows chi square on n minus 1 degrees of freedom. So, we can use some modified notation here, because I substituted here expectation of S square is equal to sigma square. So, actually I am choosing the definition of S square as 1 by n minus 1 sigma x I minus x bar whole square. So, let us use the notation so S square is equal to 1 by n minus 1 sigma x I minus x bar whole square, and let us write this S square by sigma square as say W. Then this is reducing to expectation of k times W minus 1 whole square. So, now we can find out the minimization del R by del k, that will give twice expectation k W minus 1 into W. This will give k time is equal to expectation of W minus expectation of W square. Now, let us look at these terms here. Expectation of W is equal to 1, because expectation of S square is equal to sigma square. What is expectation of W square? That will be equal to, so if I calculate say T is equal to n minus 1 S square by sigma square, that is chi square on n minus 1 degrees of freedom. So, expectation of T is n minus 1 and expectation of T square is equal to n minus 1 square into n plus 1, n minus 1 into n plus 1. So, expectation of W is equal to, because here W is equal to T by n minus 1. So, expectation of W square is 1 by n minus 1 square into expectation of T square. So, that gives us n plus 1 by n minus 1. So, this is equal to then expectation of W is equal to n minus 1 by n plus 1. So, n minus 1 by n plus 1 S square, that is equal to 1 by n plus 1 sigma x I minus x bar whole square is the best affine equivariant estimator of sigma square. So, let us take the whole thing in the perspective here for normal mu sigma square distribution. We had sigma square ml as 1 by n sigma x I minus x bar whole square. We had the minimum variance unbiased estimator as 1 by n minus 1 sigma x I minus x bar whole square, whereas the best affine equivalent estimator is now 1 by n plus 1 sigma x I minus x bar whole square. Since all of these are only multiples of sigma x I minus x bar whole square, this is the best among these two, these three. So, you can see here that the principle of invariance allows us to improve upon the given estimators, the estimators which we have obtained using the method of maximum likelihood estimator, method of moments, or by the method of minimum variance and by estimation, etcetera. Of course, in this problem it can be further shown that even this best affine equivalent estimator can be further improved, but that is by another approach. So, we will not be doing that approach here. Now, for this problem I want to give one more application here. Let us consider another loss function, say L star, in place of star let us put L 1 mu sigma d is equal to d minus mu minus eta sigma whole square divided by sigma square. Now, what is this problem? This can be considered as estimation of theta is equal to mu plus eta sigma, where eta is a fixed constant. See, in the case of normal distribution, mu plus eta sigma denotes a quantile, because here if I consider probability of x less than or equal to theta, that is probability of x less than or equal to mu plus eta sigma, that is equal to probability of x minus mu by sigma less than or equal to eta, that is equal to phi of eta, where phi is the standard normal CDF. So, if I put this is equal to p, that is eta is equal to phi inverse p, then this is the pth quantile of order p. That means, if I am considering the distribution here, then this probability is p, this probability is 1 minus p. So, this point is mu plus eta sigma, where eta is given by phi inverse p. So, this is the pth quantile. So, like mean, median, etcetera, the quantiles also of interest to be estimated to denote or to find out various locations on the distribution. Let us consider the estimation of this here. And so, consider the affine group. Now, we have already seen here that mu goes to a mu plus b, sigma will go to a sigma. So, what will happen to theta? Theta is equal to mu plus eta sigma. So, this will go to a mu plus b plus eta a sigma, that is equal to a mu plus eta sigma plus b, that is equal to a theta plus b. Therefore, d must go to a d plus b. So, if that is happening, then L 1 remains invariant. So, affine equivalent estimator if I consider affine equivalent estimator, that must satisfy d of a x bar plus b a square s square is equal to a d x bar s square plus b. So, if you choose b is equal to minus a x bar and a is equal to 1 by s, then we get the form of d x bar s square as x bar plus, because this will become a constant, and we get minus a x bar and then we put 1 by s. So, s is multiplied by this constant plus this x bar. That is the form which is the same which we obtained for the estimation of mu. Now, if you consider the risk function of this estimator, that is expectation of x bar plus k s minus mu minus eta sigma by sigma whole square, then we can write it as expectation of x bar minus mu by sigma whole square plus expectation of k s minus eta sigma by sigma whole square plus 2 times expectation of x bar minus mu by sigma into k s minus eta sigma by sigma. Now, here these terms are independent, because in the sampling from normal distribution x bar and s square are independent, and this term becomes 0. So, the problem has reduced to minimization of this term, expectation of k s minus eta sigma by sigma whole square. Now, this is a convex function of k. So, the minimization will occur when we differentiate this with respect to k and put equal to 0. So, the minimization with respect to k is achieved when del r by del k equal to 0, and del r by del k is actually equal to twice expectation k s minus eta sigma into s equal to 0. That will give us k is equal to eta sigma expectation of s divided by expectation of s square. Now, if we use the terminology used in the derivation for estimation of sigma square, we had defined T as n minus 1 s square by sigma square, then this is following chi-square distribution on n minus 1 degrees of freedom. Now, expectation of s is coming in the terms of t to the power half. So, let us calculate expectation of t to the power half. We have the density function of t as 1 by 2 to the power n minus 1 by 2, gamma n minus 1 by 2, e to the power minus t by 2, t to the power n minus 1 by 2 minus 1, where t is positive. So, expectation of t to the power half, that will be 1 by 2 to the power n minus 1 by 2, gamma n minus 1 by 2, e to the power minus t by 2, t to the power n by 2 minus 1 dt. That is equal to gamma n by 2, 2 to the power n by 2 divided by 2 to the power n minus 1 by 2, gamma n minus 1 by 2. That is equal to root 2 gamma n by 2 divided by gamma n minus 1 by 2. Now, s, here we can consider s by sigma and s square by sigma square. So, this is reducing to expectation of w divided by expectation of w square, sorry, expectation of w to the power half, because here I get s by sigma. So, this is w to the power half and expectation of w. Now, what is w to the power half that is equal to t to the power half by square root n minus 1. So, expectation of w to the power half is equal to root 2 gamma n by 2 by root n minus 1 gamma n minus 1 by 2. So, these terms we substitute here eta root 2 gamma n by 2 divided by square root n minus 1 gamma n minus 1 by 2, and then expectation of w is equal to 1. So, this is the term that we get. Of course, we can write it as eta root 2 by n minus 1 gamma n by 2 by gamma n minus 1 by 2. So, this is the best choice of k, and we are getting x bar plus, let me call this as this choice as say k star s is the best affine equivalent estimator of theta, that is the quantile. Once again you can see this is different from the maximum likelihood estimator. So, it is better than MLE and UMVUE of theta. So, today we have discussed the concept of invariance in detail, and we have seen that finding out the best invariant estimator under a certain group of transformations many times leads us to much better estimators than the conventional methods that we have discussed till now, like the maximum likelihood estimation or the minimum variance and bias estimation. Another point which is to be noted here, we have not discussed it here till now, is that there are procedures which can also lead to improvement over the equivariant estimators, but that is part of some advanced discussion. If we find time, we will be able to cover it somewhat later. So, I will also introduce some decision theory concepts such as the Bayes estimation and the minimax estimation in the next lectures.